For this year's Rosie competition, we have ventured into autonomous competitive robotics, using the power of reinforcement learning through the VEX AI competition. In the VEX Robotics competition, teams compete on a 12 by 12 foot field in dynamic head-to-head matches. A match typically consists of both an autonomous period and a driver-controlled period, with the majority of play being done under driver control.
In the VEX AI competition, it is our challenge to eliminate the driver. That's right. Matches are played completely autonomously, that is, with no human interaction. Typically, when developing autonomous robotics, a robot is taught actions in a comprehensive simulation environment. One problem, though. This is a VEX robot. This is also a VEX robot. And these are all different VEX robots. There's a reason for this. It's because the game changes every single year.
To address this issue, we created a lightweight, abstract representation of the game that focuses on robot actions instead of robot design. This allows our decision-making model to focus purely on game strategy. To enable this, we have split our robot control into specialized subsystems to separate the low-level technicalities of robot implementation from the high-level robot gameplay. Using our abstract representation, we trained a reinforcement learning model in Gymnasium to play this year's game, similarly to how reinforcement learning models have been used in the past to learn strategy games like checkers and Go. Here we have an example of a virtual agent making decisions to play a simulated match. For each step, the model uses the information it receives to make strategic decisions, attempting to score as many points as possible. After each step, a reward is given based on any changes in the score. If the action the model chooses is invalid, a penalty is given to restrict that type of behavior. After training is finished, we are left with a model that can make decisions based on the game state to maximize points.
We found that our model develops a solid strategy after about 125,000 matches, or 5 million training steps. On a standard MSOE laptop, training runs at roughly 800 steps per second. On Rosie, we can achieve 5 times that speed, at about 4,000 steps per second, completing the entire training process in under an hour. Beyond speed, we can run multiple training jobs at once on Rosie, allowing us to test different approaches in parallel. Additionally, its remote access capabilities let us train from anywhere, a huge advantage during VEX competitions where we often need to adjust strategies based on new insights about our opponents.
The Rosie competition itself has been a huge factor in our ability to pursue this project. Each of our robots are equipped with an NVIDIA Jetson Orin Nano, a compact computer designed for AI and robotics. These devices were gifted to members of the team during last year's Rosie competition. They empower the robots to apply our trained model in real-time matches, something that would have been nearly impossible otherwise. Additionally, the Jetson Nano hosts a software package called the VEX AI Dashboard. This program gathers information about the game environment and sends it to the decision model. Through the VEX AI Dashboard, we can track objects on the field and the robot's position using an Intel RealSense camera and the V5 Brain microcontroller. When processing a higher level action from the model into lower level commands that the robot hardware can execute, we break it down into smaller problems. We first generate paths on the field for the robot to follow, using a library called CAS-ADI to solve for the shortest path given the field state. We then translate the action and paths generated into simple commands the robot can execute.
With the systems we currently have in place, we have been able to generate routes for the robot to follow for the skills competition. These generated routes have been successful enough for our team to place third on the global leaderboard for VEX AI skills at the collegiate level. Our placement on the leaderboard has qualified us for the VEX AI World Championship in June, where we will face off against other qualifying teams in head-to-head matches. Before this world-level competition, our next step is to integrate our subsystems. This will enable our system to make real-time decisions in a match environment. Over the next month, before the Rosie competition, we are confident that we can achieve this goal, allowing us to have competition-level strategy during the World Championship.
Our project highlights the benefits of using a simplified environment alongside reinforcement learning in the context of autonomous robotics with physical AI. Having access to Rosie has not only enabled us to conduct the rapid development and testing of these environments, but the Rosie competition itself has also provided us with the necessary hardware to run the model on the robot. Having access to both of these is what truly made it possible to pursue this project. Moving forward, our approach contributes a unique perspective on environment design that will open pathways to flexibility in physical AI across the VEX AI competition games as well as other AI applications.